Hello students, I hope you are fine. Today our topic is equivalence classes. We'll start from equivalence relation, we'll do equivalence classes, then partitions. So let us proceed. Now let us recall about this relation, especially equivalence relation. We recall that binary relation R on a set A is called an equivalence relation if and only if the following three conditions are true. Reflexibility, X is related to X for all X belongs to set A. Symmetry, if X is related to Y implies that Y is related to X for all X and Y belongs to set A. Then transitivity, X is related to Y and Y is related to Z implies that X is related to Z for all X, Y, Z belongs to A. Now, for studying the equivalence classes, we should start from equivalence relation. Unless the relation is equivalence, you cannot get the equivalence classes. So let us start from a school situation. You see the students are standing and they are of different races. That means either they belong to different houses or they belong to different sections of a class or maybe different classes. For this particular example, I am taking them as different sections A, B, C, D. Now, I am naming the set of students as S. And I am defining a relation that students of same section. Now, certainly it will be an equivalence relation. So, now the subsets are section A, section B, section C, and section D. So, A, B, C, D are subsets of S. In subset A, all the students are related to each other. Similarly, in subset B, all the students are related to each other under this relation that belongs to the same section. Same in case of section C and section D. So, in every case, the relation is a equivalent relation. So, to these subsets, we give the name as equivalence classes. So, one equivalence class is the set of A section, one equivalence class is set of B section, one equivalence class is set of C section, and one equivalence class is set of D section. Now let us take another example. X is set of all polygons and the equivalence relation R is defined as with the same number of sides. So is it an equivalence relation? Yes. Now here we can find the subsets. So one subset is set of triangles. So that is one equivalence class because inside this set again we can verify the equivalence relation. Suppose in a triangle 1, triangle 2, triangle 3 belongs to set of triangles and the same number of sides, so this is equivalence relation. Another equivalence class can be for set of rectangles. Another can be for pentagons. So these subsets, triangle, rectangle, pentagon, are 1-1 equivalence classes. So what is equivalence classes? Anytime we have an equivalence relation on a set, this relation partitions the set into disjoint sets called equivalence classes, where each equivalence class is given by those elements that are equivalent to each other with respect to the equivalence relation. So you must have seen this, that these sets are disjoints, they don't have any common, but inside that set they have the equivalence relation. So now formal definition of an equivalence class. When we say equivalence class, it is always equivalence class of an element A. The equivalence class of A consists of the set of all x in set X such that A and X are related by relation to each other. And it is written as square box A is equal to set of all x belongs to X such that A is related to X. Now let us take an example and we will learn how to find the equivalence classes. A is a set, it contains the element 1, 3, 5, 9, 11, 18 and a relation R on A given by R is equal to order pair A, comma B, where A minus B is divisible by 4. So we have to find the equivalence class of, when I say equivalence class, it should be related to each element of the set. So I repeat the question again. A is equal to 1, 3, 5, 9, 11, 18. It is a set and a relation R on A given by A, comma B, A minus B is divisible by 4. We have to get the equivalence class. So as I told, first we have to check that whether it is a equivalence relation or not. Otherwise we cannot speak of its equivalence class. R is reflexive because A minus A is equal to 0 and 0 is always divisible by 4. So for every element of A, this is true. R is also symmetric because whenever A minus B is divisible by 4, B minus A is also divisible by 4 for all AB belongs to set A. A minus B is divisible by 4 and B minus C divisible by 4, then A minus C is also, we have already learned how to write this, and it is divisible by 4. So this is a transitive relation and it is, R is equivalence relation. So after checking that it is equivalence, then we will go for equivalence classes. So we'll take all the elements. For example, we'll start from 1. We'll check what are the other elements are connected with 1. That means we have to think of what is the number which is subtracted from 1 is divisible by 4. So 1 minus 5 is divisible by 4. Again 1 minus 9 is also divisible by 4. So for 1 is connected with 5 and 9 under mentioned the relation. So equivalence of class of 1 is denoted by square bracket 1. So square bracket 1, equivalence class 1 is the set of 1, 5, 9. And if you observe very carefully, only 5 and 9 are connected with 1. So can you think of any other number? 1 minus 3? No. 1 minus 9? Yes, we got it. 1 minus 11, that is 10, not divisible by 4. 1 minus 18, also 17, it is not divisible by 4. So the equivalence class of 1 is denoted by square bracket, and it is the set of all the elements which are related to 1 under the condition that a minus b is divisible by 4. I hope it is clear. So we write like this, that means 1 square bracket 1 is equal to set of 1, 5, 9. So we mentioned equivalence class for element 1. Next equivalence class for 3. So we'll check what are the elements are connected with 3, so that 3 minus that element is divisible by 4. So 3 minus 5, no. 3 minus 9, no. 3 minus 11, 8, yes. 3 minus 18, no. So 3 minus 11 is divisible by 4, no other element is connected. So 3 is connected with 11. So equivalent class of 3 is denoted by square bracket 3, and it is set of 3 and 11. So equivalence class for 1 we wrote, equivalence class for 3 we also wrote. Next is equivalence class for 5. It is equivalent to equivalence class of 1 because 5 minus 1 is divisible by 4 and 5 minus 9 also divisible by 4. So when once you get 5 is associated with 1, so for 5 it will be same as the equivalence class for 1. So we say equivalence class of 5 is equivalent to equivalence class for 1. So we write it in square bracket 5 is equivalent to square bracket 1. So for next element is 9. See that 9 is also associated with 1. So the equivalence class of 9 is equivalent to equivalence class of 5 is equivalent to equivalence class of element 1. So 1 finished, 3 finished, 5 finished, 9 finished, then coming to 11. So if we'll see 11 is also mentioned with 3, connected with 3. So equivalence class of 11 is also the equivalence class of 3. They are equivalent. So last is 18. So for 18, which is the element? It is same as 18. 18 minus 18 is 0, which is divisible by 4. So we got equivalence class for all the elements. So for 1 it is 159, for 3 is 311, for 5 18 is 18, and the rest are repeated. So we are getting 3 distinct or disjoint equivalence classes. So we mentioned 3 disjoint equivalence classes. Now we'll go for partitions. So first, for equivalence class of 1 is its set contains 1, 5, 9. So we say this partition 1, for second it is partition 2, and for third it is partition 3. So set 159 is called partition P1, 311 are called P2, and equivalence class of 18 is called P3. P1, P2, P3 are partitions. Now let us see some properties. If we see that P1 union P2 union P3 is whole set A, 1, 3, 5, 9, 11, 18. Now if we see their intersection, it is 5. That means partitions are always disjoint, and when they are united or they are combined, we get the whole set. Now some lemma for equivalence classes and partitions. Let A be the set and R be the equivalence relation on A. The A, we define the equivalence class of element A denoted by square bracket A. So equivalence class of A is equal to set of all x belongs to set A where x is related to A. Then for any A belongs to A belongs to equivalence class. For any AB belongs to set A is related to B if and only if equivalence class of A is equal to equivalence class of B. For any AB belongs to A, either intersection of equivalence class of A and B is phi or they are equal. So this finishes the topic. I hope you have enjoyed. Many more concepts will be continued. You can solve different questions for problem solving, and all the best for your coming days. Thank you for watching. Please share the video with others. Please don't forget to subscribe.